Hey physics, today we're looking at how Ernest Rutherford discovered the nucleus. So I want to point out before we get started that no man is an island working on science. Everyone is working with teams, and they're working like using the knowledge that's built by different people in different parts of the world even, like thinking about these things and finding different ways to experiment with them. So even though, we talk about these individuals whose names we stick to these ideas, it's not just one person that came up with this stuff. This is like a collaborative venture of like a ton of people that are working on this stuff together in different parts of the world, sometimes in the same lab too. So today we're talking about the nuclear model, which is model number 3 that we're looking at, and we are going to crumple this one up too, but there's some things that will stick here. There's some really important parts of this model that we have found to be true. So the simple model, just to review, is what we thought was true since 400 BC, since the very first people started thinking about atoms. Uniform sphere with uniform properties. Then in 1897, J.J. Thomson did his experiment, came up with a plum pudding model, which answered some questions about the charges inside of the atom. But there were some things that was wrong with it, right? Like he thought that the mass of the atom was like a blueberry muffin, where it was kind of like a bunch of positive fluff in there with these negative electrons kind of scattered throughout like blueberries or like plums in plum pudding. So Rutherford decided to test this, and we're going to get into how and why, but what he came up with is the nuclear model, which is that the nucleus of the atom is this super small, dense, positively charged part of the atom, and all around it is empty space with electrons kind of like floating around. We don't really know exactly what those electrons are doing yet, but that's what the nuclear atom says, okay? So let's look at this specifically. A tiny, dense, positively charged center made up of subatomic particles called protons. So this is our first introduction to the proton as well. There you can see that. The nucleus contains most of the atom's mass, and we're going to get into that over the next couple days also. So, mind-blowingly, what this experiment revealed is that most of the atom, by far, is just empty space. It's not a solid sphere of blueberry muffin mush. It is empty space, like with these tiny, tiny particles in there. And that really changed our view of the atom. So how did we get there? How did Ernest Rutherford figure out that most of the mass of the atom and all of its positive charge are densely concentrated in a tiny nucleus? So this is him thinking about it. He's like, I don't know about this plum pudding model. There must be something more to it. And he was not the only one thinking about this. In fact, there was a Japanese scientist whose name is, hold on a second, let me find, whose name was Hantaro Nagaoka, who was a Japanese scientist who thought that, he also disagreed with the plum pudding model, but he thought that maybe the atom would look kind of like Saturn, with a big, giant center nucleus, like the giant gas planet Saturn, and then these rings of electron around it. So that was an interesting thought. Rutherford looked at that and he thought that's interesting too. But his experiment proved something a little bit different. So let's go back into history a little bit and look at what was going on at that time. So there were a lot of experiments with radiation at that time. This was a thing. People didn't really know a whole lot about what was causing radiation, what it really was, but they knew that it was there and they could see some of its effects. So it became like this really cool thing to put into all kinds of products. Like they found radioactive substances like plutonium, like uranium. There were experiments to create new elements like americium, among others. And so these products were being put into things like toothpaste to whiten your teeth, like put into lipstick and cosmetics to brighten your face. They would put them in like alarm clocks to make the alarm clocks glow. This is hot chocolate with radiation, with radium. I mean, like, it's crazy. So at the time, radiation was cool. And Rutherford, that was his like mode of study. He wasn't necessarily into the fatty part of it, but definitely he was into the study of actual radiation and how it can be used to learn about atoms. I mean, you could even get like this thing that would put radioactive water, like, so you could drink radioactive water from your refrigerator. Like, it would put like radium atoms into your, like, radioactive stuff into your water. It was like a big deal. And I think the idea behind that was that it made you kind of like glow a little bit. But now we know that's like super dangerous, which is why we don't have radiation toothpaste or, radium lipstick anymore. But it was an interesting idea. So something else that was really cool, and this has been going on for a super long time, is in Japan, there is actually, and this is other places too, I'm sure, but there was gold foil. So give me just a second. I'm going to show you this video so you can see what this is about. So this village in Japan called Kanazawa specialized in making gold foil, which was used to coat like everything with gold. I mean, it was like a really fancy way to decorate churches and decorate shrines and decorate all kinds of stuff. So this 5-minute video, I'm not going to show you the whole thing right now, but it shows the whole process of how gold foil is made. And what is really interesting about this gold foil is that they make it so thin that it is like translucent, like the light comes through it. It is 1.5 microns thick. Let me fast forward a little bit so you can see some of the interesting parts of this. So, I mean, they wrap it all up. Oh, here's that machine. So it's just this like, they start off with like coins basically that are about maybe quarter size, maybe a little bit bigger than that. And then they put it in between these sheets of paper to separate it. And then it gets smushed and smushed and smushed until it is so small. I think I remember reading that, it's tiny. Yeah, it spreads out so that it's a bit bigger, but then they cut it all perfectly to size. It's super artisanal and awesome. So Rutherford knew about this. And maybe I can show you a part that shows like where you can see like the light coming through it. It's really amazing how thin this stuff is. You can see how it just is like, okay, now maybe this is the part where you can see. There's a part in here where you can actually see how the light goes through it. I mean, it's really amazing because gold is a very heavy atom. It's got a lot of protons and neutrons in it. So, okay, so for reference, because we're talking about tiny measurements that you probably don't hear about very often, 1 millimeter equals 1,000 microns. 1 micron equals 1,000 nanos or nanometers, and 1 atom is 0.1 nanometers. So even though this is like 1.5 microns thick, it's still like way bigger than an atom, but it's thin enough that we can see the results of this. We can see the results of this experiment. It works for what we need. So Rutherford looked at, he was like, what would happen if I bombarded a super thin sheet of gold foil with radioactive alpha particles? So what he's doing is taking this radioactive substance that's inside of this sheltering thing that blocks radiation, but there's a piece cut out of it so that the radiation can kind of stream out this one part, and it's going to be aimed directly at this super thin sheet of gold foil. Okay, so let's talk about first of all, what is an alpha particle? The alpha particles are the particles that are being shot out of this radioactive material into the gold foil. They're positively charged. So this is how this happens. When an atom gets too big, it becomes unstable. And so then what happens is that there's not enough of what's called the strong force, which you're going to hear about pretty soon, and pieces of that atom shoot off. And one of those pieces is called an alpha particle. And what it is it's a helium atom that has no electrons. So it's just 2 protons and 2 neutrons, which you're going to hear about pretty soon. So positively charged because there's no electrons there, and it's going to shoot out at the gold foil. And just so I know this is a terrible picture because it's so blurry, but an alpha particle is the least strong kind of radiation. Alpha particles will stop at paper. Beta particles are another kind, and they will go all the way through skin. X-rays are a kind of radiation that was discovered at this time. X-rays go all the way through skin, wood, and they stop at cement. Gamma radiation goes all the way up to cement. Neutrons are another kind of radiation that can actually go all the way through cement, and that is what kind of radiation I believe occurs from atomic bombs. So Interesting things. So according to the plum pudding model, it seems like positively charged alpha particles should, and I want you to think about this for a second to yourself, if we're shooting positively charged particles at this plum pudding model of the atom, what are they going to do? Do you think that they will go right through? Just kind of bust through those negatively charged particles, bust through that positively charged fluff? Or do you think they're going to bounce off? So Rutherford had that question too. He was wondering what would happen in that situation. So I'm going to show you this experiment that he did. Here we go. So we have these positively charged particles, alpha particles, coming from this radioactive source, beaming at this fluorescent screen. So when they hit the fluorescent screen, the screen lights up. That's what that means by fluorescent, is that the alpha particles cause it to light up. So then because you can't see the alpha particles, they're too small on their own, but you can see where the screen lights up. So you can see that before that gold foil was there, it goes straight through. But then once you put the gold foil there, it doesn't just bounce off, it doesn't just go straight through. A lot of the particles go straight through, but some of them do bounce off. And what they're doing is they're hitting the nuclei of those atoms. So let's look at it again. Let's look at this one. So here we have that beam of alpha particles in this fluorescent screen. It's causing the fluorescent screen to light up because they're bouncing off all kinds of which ways. Every time one of them hits that nucleus, and like I said, like most of them are still going straight through, and that's what is kind of like interesting and puzzling, like how are most of them getting through? But then some of them are bouncing off. So it turns out these nuclei and these atoms, and all nuclei and all atoms, are super tiny. They're like 1/10,000th the size of the whole atom. So you can see these alpha particles bouncing off only when they hit that super tiny nucleus. Okay? So if you would like to, you can check out this modern day replication of this famous experiment, which was done by a modern physicist. And a few things are different here. One of them is that instead of having a fluorescent screen all the way around, this physicist just has like a sensor, and it makes a bell ring every time one of the particles hits that. So it only is making the bell ring when it hits like right here on this sensor. But you can still like hear like how often it hits there. Maybe we'll see just a little bit of this. Oh, it's got Spanish subtitles. Cool. So this is the physicist. Okay, so you can see what's happening there. Let's listen to it a little bit.
It was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing them at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target.
So if you've ever heard of the Hadron Collider, that is one of the main ways that people are still studying particle physics, and it's fascinating how that works. And this all comes from Rutherford's experiment. So let's look at another picture of this. We've got the alpha particle beam coming through the gold foil, mostly coming straight through, but some of them are bouncing way back. They're hitting the fluorescent screen whenever, and it lights up the fluorescent screen whenever it hits it. I got to finish up here pretty quick. Hold on a second. So I only have 40 seconds left, but basically the advantages here are that most of the atom is empty space. That explains that. We learned about protons. We learned about the small dense nucleus. The disadvantages, things that we don't know yet. We don't know how electrons are arranged yet. And we also don't know how like-charged positive protons can stay so close together in the nucleus without flying apart. So, are you convinced that this is the final model? So now you're going to go to the Google form, the small dense positively charged nucleus. Good luck.